We are constantly surrounded by sound. We even have a highly specialized opening in our heads for making sounds that may be meaningful to other people. We communicate through sound. In fact, it is our major means of communication. When we disturb the air in any way, we create sound. The slightest motion of our bodies disturbs the air around us, and we produce sound. When we raise our hand, we compress the air in its way, and that compressed air front will travel away from us at the speed of sound, which in air is about 740 miles per hour. When we make periodic movements with our hand, the sound becomes a note. By sound we mean here any random acoustical disturbance that may be composed of many different frequencies. A note, on the other hand, is the sound of a single frequency. We call this kind of sound infrasound, that is, sound below our level of perception. However, when a fly or a mosquito beats its wings, it does it fast enough and we sure can hear it. The rapid flapping of its wings produces evenly spaced compressions and rarefication of the air that become audible to us. In short, a fly or a mosquito is producing a sound or a note. Let us try to make sound in a less obvious way. We shall take a short piece of wire, connect both its ends to a battery through a switch, and close the switch. We were told in school that three things happen. 1. That electrical current will run from one side of the battery to the other. 2. That a magnetic field perpendicular to that current will shoot out and expand all the way to infinity at the velocity of light, which is about 186,000 miles per second. And 3. That the wire will heat up slightly. They probably did not tell us. 4. That when the wire heats up, it expands, and by so doing it will clearly force the air out of its way and make a kind of sound. Or 5. That as the mass of the wire is accelerated in this way, it will produce gravitational waves, since any time a mass is accelerated, it will broadcast gravitational waves which will again expand to infinity at the velocity of light. Some will say that the gravitational waves will certainly be almost infinitesimally weak, but that does not worry us as long as they are there. So our action of closing the switch has been broadcast, theoretically at least, to the outer limits of the atmosphere around the Earth due to the movement of the air, and was broadcast all the way to the end of the universe by the expansion of the magnetic field around the wire and by the gravitational wave due to the wire's acceleration. The purpose of this example is to show how in principle even our smallest, most insignificant actions will be broad, cast far and wide, and thus influence something or someone, whether that something or someone is aware of it or not. We should look now at other effects of sound. If we stretch a string on a frame, then pluck the string in the middle of its length, we shall see the outline of the string in the extreme positions of its movement. It forms two symmetrical arcs as shown. These are standing waves. We get such waves only when plucking the string at distances that will divide the string into integral numbers. The frame length corresponds to half a wave, while in Figure 2b the frame accommodates a full wavelength. The string has a point in the middle at which the string is at rest, and two more points at which it is attached to the frame. Such points of rest are called nodes. All the other points of the string are vibrating up and down. When the nodes along the string appear stationary and fixed while the rest of the string is vibrating, we call such a behavior a standing wave. Suppose we now take a thin sheet of metal, clamp it at one edge so that it stays in a horizontal position, spread some dry sand evenly over this sheet, then take a violin bow and draw it over one of the free edges of the sheet until it emits a note. Very soon we shall see that the sand grains are collecting on the sheet in a symmetrical pattern. As we apply the bow at different points along the edge of the metal, we shall get different and quite beautiful patterns on the sheet, with a fluid and disperse particles in it with the same specific gravity as the fluid so that they stay dispersed in the fluid and do not sink to the bottom. Then, by vibrating the walls of this box from all 6 sides in a synchronous manner, we could cause these particles to aggregate in a symmetrical 3-dimensional pattern. This pattern will look just like a highly enlarged crystal if we assume that the aggregated lumps are analogous to the atoms in a crystal. We have again produced a standing wave pattern in this box, which is a 3-dimensional analog of the standing wave in the string and the metal plate. At the same time, we have produced a 3-dimensional object analogous to a basic building block in nature and a highly ordered crystal. And we have done this simply by applying sound to an amorphous, disorganized suspension of particles. In the box, we have set up an interference pattern of standing waves, which we will soon explain, that governs the position of the particles. In short, by using sound, we have introduced order where previously there was none. It may occur to us that a crystalline structure may be seen as representing sound interacting in a volume. Is it possible that the orderly pattern of atoms in matter is the result of the interaction of some kind of sound waves in matter? Superposed sounds now let us go one step beyond and see whether sound can also be used for storing information or knowledge. A shallow, round pan and 3 pebbles are all we need for this experiment. Fill the pan with water. Now drop in the 3 pebbles simultaneously, as shown in Figure 6, and watch the ripples spread in the pan. Each pebble is the source of waves spreading evenly across the pan. Let us neglect the wavelets reflected back from the walls of the pan. These waves cross each other and create quite a complex pattern of wavelets on the surface of the water. They look pretty chaotic to us. There is, however, an order in this apparent chaos. All that has happened is that the wave produced by each individual pebble expanded and reached the edge of the pan. In so doing, the waves have crossed and interacted with each other on the way to the edges of the pan. This interaction asterisk created a complex pattern that is called an interference pattern. If we carefully analyze this pattern, however, we can trace back each wavelet to its source, the pebble. Let us now quick freeze the surface of the water in the pan and lift out the resulting rippled sheet of ice. We are holding in our hands a record of the interference pattern of waves, or we may even call it a hologram. F** superposition is included in the broader term of interaction. Hologram is usually a flat photographic film on which information is recorded about the shape of the object in the form of a wave-front interference pattern. When this film is illuminated with the same light under which the information was originally recorded, the wavefront is reconstructed, and the image appears in space as a 3-dimensional object identical in shape to the original object. Seacock, Winston E., Lasers and Holography, New York, Doubleday Anchor, 1969. London, Heinemann Edduk, 1972. Interference patterns and beat frequencies. In order to clarify what an interference pattern is, we have to learn 2 additional properties of sound in its different forms. 1. Constructive and destructive interference. And 2. Beat frequencies. Let us take the first one. You will see what happens when 2 wave patterns of identical frequency and amplitude or wavelength meet. Let's try to superimpose them on each other. We see that the hills and valleys of the frequencies in rows and B match each other. If we superimpose them by measuring their heights or amplitudes from their respective baselines, then we find that hill matches hill and valley matches valley. And when added up, they produce a waveform twice the height of the original waveforms, as shown in row C. This is known as constructive interference because it builds up the amplitude. If we now look at Figure 7b, we find that hills match valleys and valleys match hills. And if we add them up, we shall find that they cancel each other out, as the flat line in row C indicates. This is known as destructive interference. This is what is happening in our pan of water. If we look at the ripples in the ice sheet, we shall find that where hill meets hill, we end up with a hill, double the original wave height, and where hill meets valley, we find just a flat spot. This is the nature of an interference pattern. However, many forms of interference patterns are possible. We may have them in a single dimension, as when we vibrate a string, or in 2 dimensions, as in our flat pan, or in 3 dimensions. Beat frequencies. Now that we know what an interference pattern is, it will be relatively easy to understand a beat frequency. In Figure 7c, we see a frequency in row I, let us say it is 50 cycles per second, and a frequency in row B, which let us say is 60 cycles per second. If we add them up as we did before, we shall discover an interesting phenomenon. Row C shows the result of adding the 2 frequencies. What we see is a pearl-shaped waveform superimposed on top of our A and B waveforms. Starting from the left, we see that in row C the amplitude, wave height, is low where the hills and valleys oppose each other and high where both waveforms coincide or reinforce each other, which results in constructure interference. The wave patterns are said then to be in phase, to use a technical term. Now, as we move to the right, we notice that the A and B waves gradually go out of phase and the hills start facing the valleys, thus opposing each other, which means that a destructive interference is occurring. This destructive interference reaches its maximum in every fifth cycle, forming a narrow waist in the amplitude or volume of the sound at those points. The Perley pattern in row C will therefore be a modulation of the basic sound, which has fixed amplitude. Modulation means a change that is being caused in an otherwise smooth or even behavior. In our case, it means an increase and a decrease of the amplitude or volume of the 60 and 50 cycle per second sound. This modulation will occur 10 times per second, with minima occurring every 6 cycles. This 10H* modulation is called a beat frequency and is the difference between the A and B frequencies, or 60 Hz minus 50 Hz equals 10 Hz. Were we to make a 10 cycles per second sound in B, a 12 cycles per second sound, we would then have a 1, 2 minus 10 equals 2 cycle per second beat frequency imposed on these two basic frequencies. The knowledge of the SETWOP rope or ties of sound will be important to the end of this book. Note that the difference between the two fast frequencies produces a third frequency that is much slower than the first two. This, then, is a beautiful device for converting high frequencies to low ones.